Olá, pessoal, boa tarde, bem-vindos a todos e a todas aqui no nosso seminário de mecânica do Departamento de Matemática da Universidade de Brasília. É um prazer tê-los aqui conosco. Então, eu quero lembrar a todos, mais uma vez, que esses seminários são abertos, tá bom? Então, se você não recebe os meus e-mails de anúncio dos seminários, por favor, coloque o seu e-mail no chat e eu adiciono vocês à lista de e-mail, tá bom? Os seminários são extremamente informais, então, por favor, interrompam o palestrante se vocês tiverem alguma dúvida, tá bom? Ele não vai ver a mão levantada, então, por favor, abra o seu microfone e interrompa, interrompa a palavra dele se for necessário, tá bom? No final da palestra, nós também teremos um tempo para conversa, para discussão, tá joia? Vocês podem perguntar durante ou depois, como vocês preferirem. Eu quero apenas lembrar que essa palestra está sendo gravada, a sua participação e a sua permanência nessa palestra é um consentimento para que sua voz e sua imagem sejam publicados no canal YouTube do nosso programa de pós-graduação. Se você quer continuar, mas não quer ser visto nem ouvido, por favor, desligue seu microfone, desligue sua câmera e interaja conosco pelo chat, tá bom? Sua permanência é um consentimento para ficar aqui. So without any further delay, I would like to introduce you to Mazi Jalaal from the Institute of Physics of the University of Amsterdam. He has just started there and is starting a very nice fluid lab, whose website is there. You can see on his presentation. And Mazi will talk to us about Newtonian and non-Newtonian thin films. Mazi, thank you so much for coming to Brasilia, even if virtually, to give this seminar. We are looking very much forward to it. You have the word. Thank you very much.
Thanks so much, Barry. Thanks so much. I much appreciate the invite. As you know, I wish I was there in person, but hopefully sometime soon. I hope everyone is doing fine. So, yes, so I'm going to talk about Newtonian and non-Newtonian thin films. I know this is an informal seminar series, so please interrupt me any moments. I would love to take any questions the moment you have. The main motivation of my talk today is basically the industry of coating. Just to give you a brief introduction, that on some of the available coating methods, some of them are basically droplet based, like sprays or inkjet printers, that you deposit droplets one by one, you form a filament, or then you put more droplets on top, and you basically cover a solid surface with liquids. More common methods that are more classical in a sense are includes deep coatings. When you have take your surface, you dip it inside the liquid, and you take it back, and then there is this thin film deposited on top of your plate. There are many different coating methods. Some of them are actually reviewed by Rorschach in some 2 annual review papers that you can have a look if you're interested. My main motivation to get to this business of thin films and spreading and coating was mainly due to the industry, a very emergent industry of 3D printers. In particular, the type of 3D printers that is known to as extrusion 3D printers or fused deposition 3D printers. What they do, and here are 3 examples of them: plastics, clays, and food. The way they work is basically to have a nozzle, and you put liquids in it, and you extrude it on a surface. The way I typically see this type of 3D printers is this. So you basically have a pressure sensor that in this case is the hand of the person. You have a nozzle. You have a liquid that is typically very non-Newtonian, has viscoplastic yield stress in it. I'll come to it and defines what I mean by viscoplasticity. And you deposit your liquid on a soft or hard substrate. In the real extrusion 3D printers, you typically replace the person's hand with a robot, and you program the robot, giving them the CAD file and translate to a code, and then the robot does the job for you. So here is an example. I'm using a non-Newtonian fluid, and I'm basically writing a few letters on a surface. So the robot, the nozzle is in purple, as you can see, goes around whatever I told it to print, it prints, and then when it's done with the first layer, it deposits the second layer, and you keep doing it, and you can basically also do 3D printing with this. Okay, so this was my main motivation to study spreading of liquids on a surface and see how do they spread. And this is basically also shaped the outline of this talk, which has two parts. In the first part, I'm trying to address this relatively classic problem of Newtonian fluid spreading on solid surfaces, and I hope I can show that there is still some surprising facts there. And in the second part, I will talk about viscoplastic fluids and their spreading, because that's more relevant to many applications, such as 3D printing. Okay, so what is the problem? So the problem is what I call a simplified spreading problem. So in T0, or at time 0, I have a solid surface. I have a surface that is pre-wetted by a thin film of the material. Let's call it with the thickness h infinity, and then I deposit a droplet on it, and I see how the droplet spreads. So let me tell you what happens at time infinity already for Newtonian droplets. So nothing stops the droplet. The droplet keeps moving and spreading due to either surface tension forces or gravity until you get a very thin flat film. Okay. So the question is, so what is the dynamics, and how can I understand? I can go from time 0 to time infinity, and what happens in this process. Okay. So one way that people have approached this problem is by mathematical methods, is to basically write a governing equation, which I comes to it in a second, but also to look what happens at the edge of the droplet. So this is where my macroscopic millimetric droplet, let's say, is merging to this pre-wetted thin film, let's say around few micrometers. And basically the question is, how does this droplet merge during the spreading to the thin film? So what happens, one question that we try to answer more specifically is that what happens in the vicinity of this so-called contact line, and I would emphasize this is a macroscopic contact line. So in my problem, the droplet never really touch the surface, right? Because there's this pre-wetted film. But if you look, in reality, if you look very far, so you don't see the pre-wetted film, and it looks like the droplet is completely wetting the surface. Okay. So one very common way to approach this is through the so-called lubrication equations, or shallow equations, or in the shallow limit. So you start from continuity equation and momentum balance. So I assume this audience are very familiar with it. The first equation is conservation of mass. The second equation is the conservation of momentum. You have non-convective term, convective term and nonlinear terms on the left-hand side, and there is the gradient of your stress tensor. If it is Newtonian, it's more simpler, and then there is body force. The key assumption in this so-called shallow equation is that you assume you have a film that your horizontal scale is order L and your height is one order epsilon smaller. So your height is much smaller than your length scale, and you can basically use that aspect ratio epsilon as your small parameter and do perturbation analysis and arrive to this so-called thin film equation. So I don't do the derivation because it's very well-known since the time of Reynolds. And if you're not familiar, there are actually huge body of work how to arrive to this equation and different forms of it. There's a very nice annual review modern physics paper by Oron et al. But all these names that I listed here have worked on the topic, and there are many more.
Mazi,
this equation.
Mazi,
Yes.
are your equations depth averaged?
Yes, exactly. So H, yeah, exactly. So H, let me explain a little bit what are these equations. So as you mentioned, I mean, these are basically if you insert this epsilon here and you basically get this equation scaled, you end up with a lot of epsilon square. And if I'm not, if I remember correctly, epsilon to the power 4. So you have a small term, you get rid of them, then you end up to simplified momentum equations, and then you do the depth averaging over your height h, which is here. And that ends up to this single partial differential equation. So h is the film thickness, and the left side is basically time derivative of it. On the right-hand side, I wrote these equations, by the way, for the axis symmetric or polar coordinate, because that's the equation I'm going to deal with. You can write it for much easier way for 2D. So it's polar coordinate. That's why this 1 over r shows up here, and this r. So these are Jacobians in a sense. And then you have the pressure gradient. So P is my pressure, and H cube is somehow my, you can call it a diffusive term or diffusion term. It is somehow a diffusion equation if you think, or if you look at it carefully. So
why don't you worry about velocity and you convert everything into pressure?
Well, you depth average, right? So velocity is somehow there. So your vertical velocity is an order epsilon is smaller than your horizontal velocity. So in a leading order, you only care about horizontal velocity in a sense.
Yes.
So that's basically your reduced momentum equation in a sense. And when you do this, basically you apply the kinetic conditions. You go from velocity in a sense to height. So velocity is somehow hidden there. But
height, yeah.
Exactly. Indeed. So your velocity is basically simply is a unidirectional parabolic. It's a parabola for each r in a sense. If you want, you can actually, if you have a height, you can immediately get the velocity.
Yeah, you can reconstruct. Okay.
Exactly. Exactly. And also to higher orders, you just need to keep the higher order terms. What is important is that this pressure here has 2 terms in it. So the first term is relatively, looks at least in a sense, so it's B times H, so it's first order. So I call it first order derivative because we shouldn't forget about this derivative here, right? And also this is PR. So B is my bone number. So bone number is a non-dimensional numbers that compares gravitational stresses to surface tension stresses. So 2 things drives my Newtonian thin film: surface tension and gravity. So gravity acts like a body force. It comes to my thin film equation like with this term, and this term, which is higher orders, and this is more like a devil term here. Because this is second order already, you take another derivative of it, it becomes third order, and in the end you have a 4th order partial differential equations. Okay, and this term of the surface tension one comes from the curvature of your film. So the higher the curvature it is, the higher the capillary pressure, and then it wants to, in this case, flat that free surface. Okay. So this equation is one of my very favorite equations, and now in this talk, I try to dig into a little bit more how we can, how people have tackled this, and how we like to solve this equation. Okay, so this is what I showed you now. So one very neat thing that people done in 90s is that you can, let's imagine if I go to the contact line of my droplet, I can at least do some leading order. I can assume gravity is not important. Therefore, my bone number goes to 0. Therefore, this term vanish. I can also jump to my co-moving frame by this change of variables. So zeta is my new r, in the sense that I go to the big R. So big R, if I come back for a second, so big R, sorry, I had to show it, is my basic radius. So I'm in this equation, in this formulation I'm going to show you now, I'm going to basically zoom in as I did here in this area, so which is, this is the center, this is my capital R. So let's move back to these equations. All right. So beta is 0. So B is 0, and zeta, with this transformation, I move to this moving frame at the contact line of my droplet, and then I define this new variable G, which is h over h infinity. So it's basically normalized height of the droplet. If you do this, and from these equations, you can also asymptotically get rid of some of your 1 over r terms, because r goes large, and you end up to a new differential equation. So this is, again, I didn't do the algebra, but it's relatively easy to come by this transformation in this equation. So now I have a nonlinear third order differential equation. G is again my normalized height of the thin film. And on the right side, I have two nonlinear terms, g to the -2 and g to the -3. And you can imagine if g goes as small or big, you can get rid of each of these two, one of these two, right? Depending on the limit that you're in. So what does that? So I call it the full solution in microgravity, because if you remember, I got rid of my gravitational effects, and this is the solution that you get. So this is you can imagine this is my big droplets that I have. So I solve this by finite difference. You can do it with any numerical method that you like. And this is my thin film. And you don't see it, but if I zoom in, you will see these undulations. So when the droplet in the macro, the large limiter and the macroscopic droplet is merging to my prewetted film, it goes through these undulations, which is very interesting. The solution on the left is asymptotic solution that you can get with some logarithmic blow up that I'm not going to talk about that. What is very intriguing for me is actually these undulations. And funny enough, for a Newtonian droplet, there's always this minimum of undulations that goes to the point 82. Okay, so this is a number that you can get numerically. You can look at the problem from a little bit of the dynamical system perspective, if you wish, and look at the derivatives. So this is the same curve I'm showing here. Now this time I'm basically going my second derivative and first derivative. Both of them are going to this attracted at 0 and 0, which is my flat thing. Okay. Again, what I want to actually if I want to summarize, if you're interested, this, as I said, has been done over 30 years ago by Tock and Schwartz in this very beautiful, elegant SIOM upright mathematics paper. It's a very neat paper. If you're interested in thin film, if you're working on it, I'm sure you know about it. But if you're interested, I think it's a very good paper to start with. So here is somewhat a summary. So if you have a Newtonian droplet merging to a thin film while spreading, what will happen is that you will form undulations. And through this type of analysis, or some sort of asymptotic analysis I showed you, you always get this minima that is 0.82. And you also can search for the wavelength of these undulations. And that can come from linear stability analysis or simpler methods that looks like this. You get that again, this big factor 5.03, and your wavelength depends on your h infinity, your film thickness, and your capillary number. So capillary number compares somehow the speed of your contact line with surface tension and viscosity. In fact, how much dissipation you have due to viscosity and capillarity. Okay, so we had these two parameters from this thin film. I knew it actually from the work of Tock and Schwartz. We did a little bit more, but we pretty much replicated there. And we were interested if we could actually see this in the lab through experiments. So our idea was, okay, so let's go to the lab and try to do some experiments. Our experimental tool was a device called digital holographic microscopy. is basically an interferometer combined with a holography technique. So how does it work? You have a laser that you pass it through a splitter. So you split the laser to one reference light, and the other light that comes all the way, goes through an objective, hits yourself, your droplet in this case, comes back and does the interferometry with your original laser. Okay, there's some very beautiful mathematics there too that I don't get to it. But all you do is indeed you get the interference between your reference signal and the signal comes back from your droplet. So this is nothing special. It's basically a Mach-Zander interferometer invented by Ludwig Mach and Ludwig Zander, both Germans. Some historic note that I didn't know and I found during this research was that Ludwig Mach was actually the son of the famous Ernst Mach. This is the Mach, very famous for the Mach number in compressible fluids, and the son actually took the place of the dad. So these are same libraries, so he literally took the chair. Okay, so we used basically Mach-Zander interferometer. We combined it with this holography, and we could, with using this device, we can actually resolve thin film heights up to nanometer resolution, if you want. So I'm going to show you one example of experiment. Okay, so what I'm showing you is my field of view in the experiments. Looks completely uniform because this is my uniform pre-wetted film. Right, so this is around 10 micrometer liquid film, and there's no interruption. So what I'm going to do, I'm going to deposit a droplet on the corner bottom left, far from actually this field of view. Let the droplet spread and look at how fringes are formed. So here's a video. I hope you can see it from me. So the droplet is spreading, and now you see these fringes are forming. So this area is my thin film. This area that you see basically speckles and noises is basically the droplet is too steep that I can't see. I cannot resolve that slope with my device, but these fringes are perfect actually to resolve the height. So what we've done, we get one of these pictures, we go through the cross section, and then we resolve for the height. So this is the signal I get. So this is H in micrometer. So this is 12 to 14, so this whole height is only 2 micrometer, and this is X in millimeter. So this is extremely shallow, what I'm observing, right? And like I said, a lot of this data is basically noise corresponding to this area here, but I'm lucky enough, or we were lucky enough to see these undulations neatly when the droplet actually attached to the thin film. So that was perfect, because I have my H minima from the experimental data, and I can also I cannot read the full lambda because even the resolution of such device is not enough to read the full lambda, but I can get half lambda, so that's enough for me to compare to the theory I just showed you. Okay, so that was time for comparison. We started with H minimum, and this was a time that you think you know everything about Newtonian fluids. You do experiment and you find out you actually don't know. So this is H minimum over H infinity. So in the equations I showed you G as a function of capillary number, and we also changed the thin pre-wetted film thickness, the initial pre-wetted film thickness. So what we saw was that at very low capillary number, it looks like this minima is going to 1, meaning the undulations are disappearing. And then as we increase the capillary number, they start to increase. And if you remember, this 0.82 was my asymptotic results, right? So as capillary number increases, I'm getting closer to that prediction of lubrication theory. And then something super strange happened. And as we increase capillary number, the waves or these undulations start to disappear again and going to 1. So remember, H mean over H infinity 1 means flat surface. So it looks like a flat surface at low capillary number, and it comes down, it's approaching our favorite number, 0.82, but again, it suddenly decides to vanish.
Mazi,
Okay.
can I ask a question there?
Absolutely.
So your governing equations
Mhm.
that you presented, they had a bond number on it.
Yes.
And now you're presenting your results in terms of a capillary number.
Yes.
So I assume that your equations, they are inviscid, right?
No, the equations are viscous. So capillary number has a viscosity in it, right?
But not bond.
But not bond. So there needs, if you want, I mean, I can come back to the bone number discussions, because that brings,
right.
I actually just escaped those slides. But remind me in the end, because
okay, all right.
give you the key, but remind me in the end, and I will tell you why bone number brings even more confusion to these results.
Right. So the problem that you're not matching the asymptotics, is it because, so I was going to ask whether it was because the fluid was viscous, but it's not because the fluid is viscous then. It's something else. Okay, go ahead. Go ahead.
So then what we repeated this experiment. So this puzzled us. So with Carola, the student worked with me in this project, we repeated this experiment and we found out it seems to be there is a critical capillary number actually, that above these waves suddenly disappeared. And that was a moment we were really triggered. And that was a moment we thought, okay, maybe lubrication equation, or what we call shallow equations, are not actually enough. So what we did was searching for new solutions, and and that's where I hope I can answer Yuri's questions too, that why we're not matching, our experimental results doesn't match asymptotic. So what we did was like, okay, lubrication theory, I mean, it's famous that it's asymptotic limits, it must work for the small capillary numbers, it must work for shallow limits, so maybe there's something missing there. So let's try Stokes equation, where we don't make such assumptions anymore. So we did that. So we basically equation in its stream function form. So I define a stream function psi, which is basically in terms of velocities, the derivative with respect to y, or the negative of derivative with respect to x, and then you end up to biharmonic equations, therefore of psi. Okay, so this is my problem again. I have, but you can include gravity if you want. We did. You have a thin film, height function h, and now you have a boundary condition on top. Your boundary is a stress-free, right? So your shear stress defines like this, and in the string function form defines like this, is 0. And you also have the combination of hydrostatic pressure on the surface and also the viscous stresses with the jump of the capillary pressure, right? Gamma HXX. On the bottom, you basically have noticed the boundary condition. We just move in a co-moving frame. I'm now moving my bottom boundary. So I'm trying to solve the same problem, but instead of thin film equation, I'm trying to tackle with Stokes equation. Okay. So what did we do? We basically did linear stability analysis. So you basically perturb your system, your height h, with your stream function sigma, and your pressure p. We went to first orders, and what you arrive with simple linear stability analysis is this dispersion equations. So which has such a form, right? So my bone number is now looks a little bit different, so that's why I'm writing it in a different form. Note that there is an imaginary part on the right, okay, and then there you get this complicated sine hyperbolic, cosine hyperbolic on the left side. It's always easier to look at the curves, so I'm gonna show you my complex plane to tell you what's happening here. So I'm showing the imaginary parts of my sigma, my root, and the real part. So what looks like a fish? So we call it a fish bifurcation within ourselves. What is important is to notice that you get oscillations when you have imaginary parts. And if I walk on these two lines, I'm sorry, I also missed two lines, two straight line at imaginary 0, but that's not important. But what is important is that this imaginary part exists for a while, which is fine. So I'm working with over capillary number. So that's what it shows the arrows. So imaginary part exists, but there is a moment that I lose my imaginary parts. There's a capillary number that I lose my imaginary solutions, meaning I lose my undulations. And that's actually a stable point. So that is exactly 1 over pi, which is 0.318, okay? And that's my theoretical critical number if I look at the Stokes equation and linear stability analysis, okay? So does it match my my experiment? So let's go back to experimental results. So this is the curve I showed you. I told you at this red line, I lose my undulations experimentally, and that's exactly what the theoretical work shows up. If this is not enough, but this wasn't for us, it was too good actually for me to believe it. So therefore, what we've done, we actually compared with the wavelength, because we also, if you remember, in the experiments, we also had access to the wavelength, right? So this is my normalized wavelength with what I had in lubrication theory. So if I normalize it this way, I should get 5.03, which is actually works perfectly fine for a good range of capillary numbers. So lubrication equation is actually doing a great job if I only look at the wavelength of these undulations at a small capillary number. The problem was lubrication equations couldn't capture this singularity at capillary number 0.32 or something, which looked like this. And now with this linear stability of Stokes equation, which is this blue line, we can capture all of them. Okay, so in conclusion, if I wanted to say, this is not enough if your capillary number goes higher, but the Stokes equation surprisingly does the job. So to answer your question, Yuri, the problem that lubrication equation didn't work was that we needed this higher order effects that is included in the Stokes equation.
Yes.
Exactly. So while doing this actually analysis, we came up with this paper of Taroni et al. These are the team of Howell and Oliver in Oxford. This is way before us in 2012. It's a very, very beautiful theoretical paper. The title, if I remember right, is On Boundary Condition. It's also around thin films, and they also actually do very similar analysis, slightly different only. And they also come up with this critical capillary number, and now here we also provide experimental work. So I was also very happy to see that work, because it's always good to have support from others. Yes,
Mazi, your Stokes equation approximation, your lubrication approximation, there is the only hypothesis is that you are at 0 Reynolds number, right?
Yes.
So you're not solving any asymptotic version in terms of surface tension or anything. So you're just solving the full Stokes equations for your system.
Yeah, we don't solve it, right? So we didn't actually solve the
Yeah, just the stability, yes.
Just the stability analysis, exactly.
So would you know which term you would need to include on your shallow water equation to correct it?
That's an excellent question. I think you're hinting of if I want to do some matched asymptotics or things like that. Right? I don't know.
Right. Okay. Yeah.
Really, that's an excellent question. I thought about it, but I never tackled this myself. So it's really hard to say how to do that, to be honest. I mean, for me, obviously, I'm sure there are better mathematicians to answer this, but maybe in your lubrication equations, maybe if you go to higher order terms, you do better with curvature, for instance.
Yeah, I was going to say that, yes.
Yeah, maybe you can start getting it, but we didn't try, and I'm not sure if that resolved, but maybe that at some point, if you add to the orders of your equations, you should converge this way.
Yep. Okay.
I was, Yuri, I was going to suggest the same thing when.
Andrea, I lost you.
Yes. Yeah.
Andrea?
Oh, sorry, that was my fault.
Okay, carry on.
Yeah, I was going to suggest the same thing. Maybe adding the full curvature can make really difference in your problem. I have this. I don't know if you have seen this paper. I noticed that you listed Uwe Thiele as one of the references to your work. So I've worked with him in 2018, and we were able to get some really good agreement with Stokes equations and lubrication equations for coating flows by essentially adding the full curvature. It was we were able even to capture multiple solutions that weren't there before. So maybe we can try this. And I'm working on this problem at the moment, so it couldn't have been. Yeah, so I'm trying to start. I've recently started working on it with a really good student of mine, Kyle, who is even watching it right now. And that was one of the things, not exactly what I wanted to do, but I wanted to try to improve this model by either adding additional terms, incorporating additional terms into the lubrication theory, or by replacing the linearized curvature term by
with the full nonlinear one.
By the full nonlinear one. And yeah, so
I think it's a great idea. I mean, maybe actually we can talk about this. I would love to discuss more details. We recently done some, not recently, 2-3 years ago, we've done some long bubbles in microchannels. Basically, the Bretherton bubbles, which is not far from this problem. And there also, like others who tried this, adding the full curvature made a huge difference. So yeah, I mean, I think it's a great thing to do, and
I think the complication would be to get the proper shallow water equation with that ugly non-linear term in the curvature. I think that's where the problem comes from.
Yeah, indeed. Yeah.
Very good, Mazi. Thanks. Carry on.
Thank you.
Thank you. Okay, so let me jump maybe here. So here, I mean, is a overview. My presentation wants to carry on.
Yeah, we only see a black screen now.
Okay, it's coming now. Okay, so so here's the conclusion. So what we basically found out, that lubrication works fine at low capillary numbers. First order terms might be important. Then at higher capillary numbers, it seems like lubrication theory at leading order breaks. So these are great suggestions that maybe we can solve that. But a Stokes linear stability of a Stokes equation works fine. How am I doing with time? I mean, I want to get to Yuri's question on gravity.
Carry on, Mazi. Okay. It's up to you. So we're not constrained by time. Take your time and do your presentation the way you please.
Because I'm going to move to non-Newtonian stuff. So
yes.
Do just one thing about gravity. So I showed you this. So I have a slide. What about gravity? So, I'm ready.
Yes.
So this is the same equation I showed you without this first term, right? So G, if B goes to 0, it's the same equation I showed you before. And this term seems to be very innocent because, you know, the other terms are really high order. This one is just first order. So this shouldn't give me much problem. But actually, at least it gave me a lot of problem. So I couldn't find a solution for this problem asymptotically, because what happens is that you need some outer solution in your matched asymptotics, which this guy change every time. I'm sure a smart mathematician can do it, but I couldn't. So I couldn't find a solution. So this is another equation to tackle for the mathematicians in the audience. And what I ended up doing, go lazy and did linear stability analysis. And this gives you another dispersion equation. So it's the same dispersion equation you had, but now equal to a constant, which is beta or B, right? So if I look at my complex space again, so it's imaginary part, this is the real part. So this is the solution for no gravity. You have 3 roots, 2 imaginary, 1 only real one, and then you start increasing your gravitational effect, and boom, you get a critical gravity, the critical Bond number. So it looks like, at least based on this equation, that even gravity at some point will result to the removal of these undulations. It's really, really hard to do this in experiments. In the beginning, we thought the undulations that disappear in low capillary number could be because of gravity. There is still a chance, but it's very hard to confirm this experimentally because droplets become really shallow and you cannot distinguish the length of gains. Okay.
Very nice. Okay. Yeah.
All right. So with this, let me move. So I talked about in the beginning about 3D printers, and I showed you clay, plastics, and food. And then I start talking about Newtonian fluids, but the reality is none of them are Newtonian, and all of them are actually very non-Newtonian. So the type of non-Newtonian fluids that typically are used in 3D printers are called viscoplastic materials. So these are materials, something between liquids and solids. If the stress is small, they more behave like an elastic solid. If the stress is large, expose external stress on them, they behave like a viscous liquid. You can think of toothpaste if you don't know what viscoplastic fluids are. So if you don't push your toothpaste, they're wiggly and elastic solid. And if you put enough stress on it, it starts to flow, right? So that's the type of fluid that we're talking about. So if I look at my stress versus strain rate, the so-called flow curve, for a Newtonian liquid, this is a boring, boring in the sense that there's nothing special about it. It's a straight line going from the origin. The slope of this line is your viscosity. The least you can do to go to viscoplastic fluid is to shift it actually up. So there is this basically threshold now that is called the yield stress. So below the yield stress, the strain rate is 0, no deformation, and above it you get some deformation. And if this is a straight line, this is a so-called Bingham fluid. So you can write it in a tensorial form like this: gamma dot, my strain rate tensor is 0 if stress is below the yield stress, and then your stress behaves like this, basically, this line if stress is above the yield stress. Typically, you get nonlinear viscosity, like shear thinning or shear thinning and thickening at the same time, things like that in this curve. Let's ignore that because this is complicated enough, as you will see. Okay, I told you also in the very beginning that if you put a droplet on a Newtonian film, it spreads until it goes to infinity, right? So you get a flat film. But for viscoplastic fluids, it is not the case. So the droplet spreads until the stress inside the droplet comes below the yield stress everywhere. Therefore, you reach this final shape that has that features this final radius RF and final height HF. Okay, you can think of hair gel or again your toothpaste again. You let it spread on a piece of metal. It doesn't spread forever, right? It spreads until the yield stress dominates. So now there are two questions: how does this droplet spread, and what's the final shape of it? And the final shape is extremely particularly important because that's what determines the resolution of 3D printers, basically. Okay, and I'm going to give you this answer by multiple methods, but I'm going to go very simple based on the scaling law in the beginning. So imagine this is your final shape. So t went to infinity, my droplet is stopped, and this droplet has a length scale of such, and V here is the volume, right? So if this wasn't a sphere, L was the radius of that sphere. You can imagine this is a hemisphere, so your volume goes to h infinity or f squared. Okay, so now all I need to do is to balance two things. Imagine there is no gravity, therefore I can balance my capillary forces, which can balance like this in shallow limit, with my yield stress forces, which is nothing but tau naught times the radius squared. So this area is taking all the stress. As the stress is equal to tau naught, and I balance it with my capillary forces, and you immediately get a scaling law. So this scaling law tells me for this given volume, right, that RF, my final radius scaled by my length of KL, varies with the coefficients that I have no idea what it is at this point to the non-dimensional number j to the power -1/7. Okay, so what is j? J is a number that I call plastocapillary number that compares plasticity through tau naught to capillarity, which is sigma. Okay, so if your material is very solid, like your tau naught is very large, your j value goes very large. Interestingly, this scaling law shows me the final radius weakly depends on j with this power law. But that's not the only limit, though. The limit is what if instead of tiny droplets, I have a big blob of toothpaste or hair gel or cement, for instance. Then you can balance gravitational forces with yield stress forces. Okay, the yield stress forces are the same, but gravitational forces are now from hydrostatic pressure or forces, and then you get another scaling law. Again, my final radius now balances with b to the power 1/5 and j to the -1/5. Okay, and b is my bone number again that shows up rho GL2, my gravity force versus my surface tension force. This again, there's no surface tension here, right? So the only reason so if you times b to j, surface tension actually disappear. There's a negative minus here. But what is important, I wrote it this way for the sake of consistency. And this limit has been studied in very much details. The reason is people in cement and concrete industry make this so-called 50-cent rheometer that you can actually use this final radius of your spreading cement or concrete to measure your yield stress. But the question is, what if I go to smaller scales, which is the interest of 3D printers, which ends up to this new scale? Okay, so naturally you ask, what is these two prefactor omega c and omega g? And in the next few slides, I hope I can show you what they are. So I told you about viscoplastic, about the lubrication theory. I told you this looks like a parabola if you have a Newtonian fluid, and this was the equation I earlier showed you with all these names. But what if you have a yield stress? So if you introduce yield stress to your thin film, this is what happens. So inside your liquid, inside your thin film, there is a surface or a line, which I show by Y, that a stress will be equal to the yield stress. Okay, so this is a so-called yield surface. Below this yield surface, you're yielding the fluid, all right? And above this, the stress is below the yield stress, so therefore you're not yielding the fluid. So this is a so-called pseudo plug or the plug region, and this is the yielded region below this line. Okay, this complicates your lubrication theory, and your final equation now looks like this. So let me tell you what it is. So HT is again the derivative of unit height with respect to time. But on the right-hand side, next to my pressure gradient, which is the same as before, because my driving mechanism is still gravity and surface tension, I now have this y squared times 3h minus 1. So what is this? So y is this line, is this yield surface that comes out of the equation like this. So h minus j over the absolute value of the pressure gradient. The limits are more interesting. So if this line goes all the way to the h, right? So I'm basically yielding everything in my fluid. Therefore, this is h squared, and this gives me 2h, and I come back to my Newtonian limit, right? So I get my Newtonian thin film equation if y is equal to h. But the other limit is actually more interesting for us, because if y equals to 0 means the stress everywhere inside my thin film is below the yield stress, meaning nothing is moving, right? So if y goes to 0, basically, if y here goes to 0, this equality will give me my final radius. I'll come back to it later. So what can I do with this equation? I can solve it with numerical methods. We use finite difference. Here is a solution of one example. So this is my time 0 that I'm showing by my cursor. And then I let it spread over time. And as it spreads, it converges to this final shape that is this golden line I'm showing here. Okay, so it doesn't spread forever, unlike the Newtonian droplet. And I can look at this yield surface for instance, this is a snapshot that I chose, the blue line, and the yield surface is this dashed red line. Looks like this, basically. What you can see in this picture is this. If I go close to where my droplet merged to the thin film, I again see these undulations. Okay, and this undulation also persistence that even the final shape, which is this golden line, also features such undulations. So that was intriguing to see this for viscoplastic fluids too. And we start thinking how we can actually get this final shape. So if I go back to this equation I showed you, I just gave you the hint. All I need for the final shape is to look at this equation, right? So remember, P is a differential form by itself, and if I want to actually equal h to this guy, so meaning y goes to 0, I have a new differential equation. Looks simpler than this one, but if I open it up, it looks like this. So again, I have some high order derivatives on the left-hand side, and on the right-hand side, I get this sine function because the depends where my h is above or below the h infinity, and basically the sign of this constant change on the right-hand side. Okay, and that's exactly what gives me undulations in my asymptotics. Okay, so if you solve these equations, you get your final shape, which is shown here by dashed red, and I can compare it with the final shape of my numerical solutions, which is shown by white line just behind it. So they match perfectly, and there's no surprise, right? Because they're in principle they're same equations that I'm solving, just different now asymptotically in a sense. And if I zoom into this contact line, I see this is my profile, my droplet merging to the thin film. My final shape still has some undulations, and this line that looked like a sawtooth is the second derivative of the interface shape. Okay, so something that I'm not going to show you because it's full of algebra is that we prove that these undulations end at a finite radius. So they end up to a algebraic series that had finite accumulation points in it. Okay, and we then go and find the boundary condition at that accumulation point. So this is very unlike non-Newtonian fluids, because non-Newtonian fluids, these undulations kept going and the wavelength was always constant, right? So they never vanish mathematically. Of course, physically, they go to molecular scale. But mathematically, the undulations never vanish in Newtonian limits, but in viscoplastic limit, they do actually go to a finite point. Okay, so after doing these things, which took a year, we were good to actually now solve fully asymptotically the final shape. So let me give you what I mean by all these things. So I told you that the final radius balances like this. I had a prefactor, and I know the scaling to be as a variation to this plastic capillary number j to the power -1/7. So now with this asymptotic limits, I have a boundary condition on my edge. I know the boundary condition in the center, and I know my equations, okay, which I just showed you for the final shape. And now I can actually do a lot of these asymptotic solutions and somehow theoretically find omega which is my prefactor. Okay, and I put all of it without going to the detail in this graph. So this graph shows my prefactor as a function of h infinity over bone number and bone times j to the minus 27. These numbers look a little bit funny, but that was the most comfortable way we could put everything in one graph. Okay, so what does it mean? You have your you know the size of your droplet, you know the prewetted film thickness, you know your gravity if you're on Earth or somewhere else. Therefore, or you know your J number, you know your bone number, and you come to this graph, you find your omega, therefore you can find the final radius of your droplet of your 2D printer, for instance. Okay, and this line that I'm showing here is a very interesting limit where film thickness goes to 0, right? So if you have a fully wetting solid surface. Okay, so there are two interesting limits. If you have only surface tension, if your droplet is very small, here is your magic number, 1.74. You can get your final radius. Sorry, this must be RF over L. And for the pure gravity, same thing, RF over L, your final radius shows like this. So you get, and this you can actually find it exactly because your derivatives, when you only have gravity or only first order derivatives goes in. Okay, so I speed up a little bit because I don't want to go out of time. We tested these theoretical analysis and experiments. We got Carbopol solution, which is hair gel. If you want to do this type of experiments, you can simply get hair gel, put it in a rheometer, and measure your material properties. So our material are basically Herschel-Buckley fluids, have yield stress, and these are the experiments we've done. We got a nozzle, we deposited a blob of liquid on a surface, we let it relax, we know the volume, and we basically let it spread enough so we reach the final shape, and we look at the final shape. So here are 4 examples from top left to bottom right. I'm increasing the yield stress. So it's not rocket science. As I increase the yield stress, droplet spread less, as you can imagine with your with a toothpaste experiment. Okay, so it was time to compare. The moment was there, and we did it. So this is my final radius over J, my plaster capillary number. The dots are experiments. The cross is my smallest bone number, and I increase the bone number until the other crosses, basically. And the lines are my asymptotic solutions. So there are some good things. First of all, the experiments at low bone number seems to be following our scaling law, which is -1/7. And as I increase the bone number, they look like they're getting to -1/5. So that's nice. But when I compare the asymptotics with the experiment, yeah, there are discrepancies, and that bothered us. And we try to solve it, and we try to think what can go wrong. There's a lot of difficulties on doing these experiments, in particular with the small bone number experiments, because the droplets are very small. So doing proper experiments is hard. Another difficulties in such experiments is that finding in material properties, in particular surface tension of these materials, is not very easy. It's not actually trivial at all, or to find surface tension of such materials. Hence, some experimental discrepancy. But the last theoretical point I want to actually go on is that all the viscoplastic lubrication theory that I talked about, everything is pretty shallow, right? So it's literally the shallow limit. But if I go back to my experimental droplets, they're actually pretty non-shallow if I look at it. So the questions that we asked ourselves when we saw the scale was, is the discrepancy also comes from non-shallowness in the experiments? To tackle that, go now rather quickly. We decided to solve the continuity and momentum equation in its full glory. We replaced this thermal stress tensor with what is suitable for beam on plastics, the one that I showed you before. Here it is in the non-dimensional form. One technical note is that we use regularization methods to tackle such a problem, because going to zero deformation rate is not possible in our numerical methods, which was finite volume and volume of fluids method combined. And we use two open source, extremely valuable open source codes, Jerry's and Basilisk, both of them developed by Stephen Poppenet in Institute of Bern. Okay, so here's an example. This is my droplet. There is no gravity on a prewetted film. It spreads. The color shows you the log 10 of the second invariant of the deformation rate. What it means, it means that whenever it's black, no deformation is happening. Whenever it's whitish, a lot of deformation is happening. So now I can get more information on the anatomy of the flow with such a numerical methods. Okay, and what is important, back to our story, is that in the end, whenever everything is black, means my droplet is not moving anymore, so I can get my final radius. Okay, so I can go back to my favorite curve, put all the simulation results next to asymptotics and experiments, and look at it again. So there's a good, in fact, comparison with our simulations and asymptotics, but still discrepancy with experiments, which bothers us until these days. I mean, one can be very positive and look at it out. They're not actually very far from each other. We are also talking about very small differences in general when I look at the y-axis. And there are a lot of difficulties, as I said, in the experiments, but there's also a lot of technical considerations when J goes large around this area, because the yield stress is so large in this regime that the way you deposit your droplet also matters. Okay, so I want to end by this. My conclusion of the viscoplastic one is that your final radius goes with this scaling law that I presented, and your omega is a prefactor like around 2. All right, so that makes our life easy. Mm-hmm. So for future, we are working on this problem currently. We want to actually do more interaction with solids and go to more applications. We're trying to actually study 3D printing of this type of materials at zero gravity in space, and also effect of elasticity is something I didn't talk about. I acknowledge the people I work with, Boris Stuba and Neil Bamford, UBC. Most of the droplet spreading in non-Newtonian work was with them. Detlef, Jaco, and Carola work with them in the Netherlands. Jaco and Carola helped me tremendously, and in the Newtonian part I talked. Thank you so much for having me. I hope I didn't take so much of your time. These two papers include all the things, pretty much all the things I talked about today. I would love to take any questions to talk about it, if you have them.
Thank you so much, Mazi, for this wonderful talk. Thank you. So now we are open for questions, doubts, suggestions.
Critics.
Georgie, please go ahead. Yes.
First, I would like to thank you for the talk, Mazi. It was very enlightening. My question goes back. Could you go back to the first model that you were presenting, or with respect to the capillary number?
The viscous one.
The viscous one.
The Newtonian viscous one. Yeah. Sorry.
Yes. So I'm not a fluids guy. So if I make any mistakes here in the jargon, you can correct me, Yuri.
Sure.
Yes, of course,
So yes, exactly that.
Okay.
So just to see if I understood this right. So as you approach the capillary number, I believe it's 0.3 something, yes, right? 1/pi. Can we interpret this graph as if the wavelength it tends to infinity? That is, we have a flat surface, right?
That's correct. Yes.
That exactly. So what happens if the capillary number goes above this threshold? So because at first you showed us a graph where you plotted the imaginary part of sigma, right? Could you go back to that graph?
This
I
one.
believe it's 1 or 2 slides for this one. Yes, that one. So I think you have a pole, right? And that point, that red dot right there. And what happens if you increase the capillary number? It seems that the imaginary part reappears, right?
Yes.
So I think the mathematical model is showing that undulations should appear again after the capillary number increases, right? Is that correct? So
that's an excellent point. So what I also said very briefly in my talk, what this curve is missing, and it was missing in my notes also for a while, and the same question you had puzzled me, is a straight line here. So basically, you retrieve your imaginary parts, but there is a more dominant mode with zero imaginary part here that I unfortunately missed, and that is more dominant. So basically, what happens in experiments and also theory is that if you go to higher capillary numbers, you actually you never receive you never have the curves again. And since you ask, I skipped one slide, which I can show now. So when you let the droplets, so these experiments now, so when you let the droplet spread, it slows down over time, right?
Right.
Because it basically is spread. And sometimes, if you are lucky or you design your experiment very nice, you go from a droplet that is high above the spread, starts from higher capillary number, and then it goes to a lower capillary number as time passes. And here is one example. I hope you can see it, but go back. So in the beginning, the capillary number is above the critical capillary number, and it doesn't show very well. But I mean, I guess over the internet.
I think we can see it. You have no undulations at the beginning, and then those undulations
so you have no undulations in the beginning, and at some point, capillary number drops below the capillary number, critical capillary number, and you start to get the undulations.
I see. Oh, so that's very interesting.
Yeah, so this basically, even for one droplet, depending on the speed of the contact line, you can transit from undulation. And this is just like exactly like a bifurcation point that you can see in the experiments too. And
very interesting. Thank you very much. That really answers the question.
Thank you, Jorge. Very nice question. Any other questions? Well, while people
actually,
yeah, Andre, go ahead. Yes.
Sorry, Yuri. Actually, I have one. It's just I just started studying this problem recently. So what I've noticed is that you have this scaling laws, and usually when you have something like this, we can look into similarity solutions. I am aware that we have similarity solutions for Newtonian fluids in this for the spreading, but have you looked into these similarity solutions for viscoelastic fluids? Do you know if there is anything?
Yeah, viscoplastic, right?
Viscoplastic.
Yeah, viscoplastic. Yes, yeah. Viscoplastic.
Yeah, I mean that's also excellent question. As far as I know, I mean the typical rule of thumb seems to be that when you have viscoplasticity, the similarity solution starts to break down. Of course, this is not a very rigorous mathematical statement, but I'm not aware. So I don't think similarity solution exists for viscoplastic fluids. The reason being, how can I say it actually? Is the form of equation, because it's somehow singular when you have the yield stress when I look at the equation. And even when you look at the shapes, they not actually look self-similar, in fact. If I'm thinking about the same thing that we do, like a moving contact line self-similarity, or the shape of the droplets over time, self-similarity. Is that correct? Is it the type of self-similarity solution you're thinking about?
Yeah, that was. I was trying to look into maybe if I could propose something in this sense, but I still have a lot to to study until I get to a position in which I can contribute. But yeah, I think that pretty much sums it up.
Yeah,
So
yeah.
I think. Yep. Go ahead.
Sorry, Yuri.
No, I think you showed in one of your results the yield surface.
Yes.
And you can see that as R increases, the yield surface is not self-similar, right?
No,
It has a very complicated shape that does not match the free surface of the spreading drop. So yeah, you can guess that you won't have a similarity solution there.
Yeah,
I see,
indeed, indeed. I mean, there are other occasions. I guess the simpler case is the gravity currents, right? Which for Newtonian case, there is a famous corporate self-similar solutions. But I think for you can't even do it for you cannot search for similarity solution when you have a yield stress for somehow the similar reason that Yuri just mentioned. Neil Bamford has a big body of work on viscoplastic gravity currents with viscoplastic lubrication, which doesn't include the self-extension terms. And I guess he also talks about why self-similarity solution actually doesn't work, if I'm not mistaken. Even for the Newtonian case, the existence of self-similarity solution for many conditions is under question. So Tock and Short, and also King, who works tremendously on Clinton, many papers. They also, I don't remember the details on top of my head, but they have some really nice technical points on where and where not to use self-similarity, or you can't use self-similarity solution. If you remember me later, I can send you maybe some papers around that. But even for the point is, I don't think so for viscoplastic fluids, and I guess for Newtonian fluids, we also have to be careful in some occasions.
Yeah, that's one thing, and the other thing that I would like to really look into, but that would take some time, is to investigate the role of the full curvature in these lubrication equations.
Yeah.
So I have this picture. If I can show you just for a second.
Yes. Go ahead. Yes.
May I? Okay, just a second.
Yes, of course. Yes.
Just a second. So I have this. Can you see my screen?
Yes.
So we have this paper with Uwe, which was happy to see in your presentation.
I also work with Uwe. I know him very well.
Oh, so I really liked him, and I spent some time in Münster, and he really helped me. So it was essentially I think some of the ideas in this paper were in Uwe's head for a while, and we just had to write it down. So this one picture, when he showed those results, and so I have here the Stokes simulations so we're studying a coating flow on the outer surface of a rotating cylinder, and we have here the in blue in these light blue lines, we have the results of our full Stokes simulations. We have also these dashed lines, which are essentially lubrication models, the ones that they are using in the literature, which was actually predicting the existence of multiple solutions. And we realized when we looked into the Stokes solutions that they were not there. And we have this novel model in which we were incorporating the full curvature effects. So you can see that the profiles, they are quite different. And it's not the same thing, but hopefully something like this can occur in yours. So that was one thing that really caught my mind, really caught my attention. So it is one thing that I would like to try.
No, definitely helps. I mean, I can, if you look at, maybe I can share now. I mean, is it okay, Yuri?
Yeah. Yes, go ahead. Yes.
Yes. So it's the. I have to find my own paper. That's how publication works these days. So let me share my screen again. So, this time I share screen 1. Here we go. So this this is relatively now a few years old, 2016 paper with Neil Bamford's also. So here we also did this lubrication approximation for viscoplastic fluids, and there is a section. I have to really think hard to remember this. So there's a leading order residual film thickness that you get from the, and then there's a corrected film thickness that comes with the better curvature. And so what I wanted to show you was not actually this paper, but necessarily this paper, but the references in it, which is I guess 23, if I'm, or maybe these guys. So here you have a full curvature, you get, right? So you don't get only this what we call here
linearized second derivative. Yeah.
Exactly. And you do that. Do I have it here? Because if you do that, you suddenly go from a very non-matching curve to something that match really good. And I guess for this problem of braided and bubble, it is known, and here we also show it for viscoplastic ones too, that it really matters to include the higher order curvatures. So I won't be surprised if that can also help other lubrication problems. So definitely something to look at. Definitely, yeah.
Can I look into the title of the paper again, just so I can write it down?
Take a screenshot.
Yeah, that would be.
Or I can just email me or send you the paper.
Oh yeah, that would be good.
Absolutely.
Yeah, that would be. I have to write a response to some minor corrections in a paper. Maybe I can include this one as well to make.
For sure.
So I'm doing this. I have this novel model for rivulet flows, and we added the full curvature, and we're able to see some really good improvements.
Oh, that's great. It'd be great if you send me the papers. I will have a look for sure.
Yeah. Oh, thank you. That would be
very good. Very good.
Thank you.
Yeah, we plan to do a lot of experiments around this area too. If there's something that we can do with your theory, that would be nice.
Oh, thank you. I'll definitely send you the.
You should keep in touch. You two should keep in touch. Yeah.
Yeah. Thank you, Yuri.
Yeah, that's a pleasure.
Yuri, you have always some really good contacts.
That's my Tinder job, right?
Matching.
I do good matchings.
Yeah, you do.
Very good, very good.
So actually,
go ahead.
And actually, I'm working with Ivan, who I met through Yuri. So you see that it's working. Everything's working.
Very good, very good. Any further questions? Mazi, I have a very quick question if someone wants to ask a question. So your J number, that I will allow myself to call it the Jalal number. So when you define the Jalal number, there is capillarity and there is yield stress, right?
Yes.
So the last picture you showed on your presentation, where you show the yield stress, the one that I mentioned, and you had it there. You show that towards the radius, towards the drop radius, it really matches the top surface, right? The free surface of the drop. Is that right?
Yes. It goes close. Asymptotically, it goes, but doesn't go perfectly to it. No.
It doesn't go perfectly to it.
No,
yeah,
no,
because I was going to ask whether surface tension is a well-defined quantity for viscous plastic fluids, especially when you have non-yielded regions.
So that's more of an experimental question. So I'm struggling with this question actually recently more and more since my PhD time. More recently, because I like to see. So I'm talking to actually some people in our group. So maybe we can tackle this. There are work. Okay, so to be fair, there are works in France from a group in Marseille. There are work from a group here in Amsterdam, group of Daniel Bohn, group of Philippe Cousseau in Paris. They all propose methods to measure surface tension of yieldless stress fluids. The bottom line is pretty much all the current methods that you go to lab measure surface tension of water or anything fails because what you just mentioned, because nothing yields, right? They don't go to the shape that you want, because all of those methods are based on the shape. And when you have yieldless stress, your toothpaste doesn't come like your honey out of your when you squeeze it. So I don't believe there is a reliable number yet, but I can go full physicist here if I want and see what's the definition of surface tension, right? Because surface tension comes from this molecular interaction. When you add polymers, exactly, when you add polymers and they interact, I mean, the question is, I don't think we even have a homogeneous surface properties. And if that is the case or not, that goes to more like polymer chemistry / physics. And I don't know. I think I personally believe it's a very interesting question, but I'm of course biased. So I don't know if anyone pays us money to study that detailed technical question. I can't hear you, Yuri. I guess you're muted.
Sorry. Yeah, definitely. Yeah. I was going to say that because viscoplastic fluids, I do a lot of granular. And a viscoplastic fluid is the very basic model for a granular model, a continuum granular model, right? And there is no such a thing as surface tension in granular materials because the particles are too big, right? So there is the van der Waals forces that act and generate surface tension in liquids they are not there. They're too weak in this granular scenario. So I was wondering whether I would expect to see these ripples in granular materials, and I think you won't, right? Because there is no such a thing as surface tension. And then that made me think, well, what is the surface tension of a yield stress fluid then? If it's yielded, then it's a normal Newtonian yield stress, a normal Newtonian surface tension, right?
In principle, surface tension should be independent of your mechanical properties in general, right? So it shouldn't it shouldn't depend if you're solid. I mean, solids also have apparently yield stress. I mean, people talk about that, but it should be independent of if you're yielded or unyielded. There are two different. I see them as two different effects.
That's interesting. Yeah.
Back to granular medium. Yeah, I'm not expecting granular medium as have a significant surface tension because they're simply too large.
Yeah. And then we won't see these ripples if we have a column collapse, for example.
Yeah, probably not. Yeah, probably not, because in gravity currents, you don't. When gravity don't see them.
Yeah. Very good. So do we have any further questions? I think we've kept Mazi for a long time already now, but if we have more questions. Okay, all right. So Mazi, thank you so much for your presence, for your talk. It was very enlightening. I think it was very fun. I think we had very good questions also from the audience. So I'm very, very pleased with that. I can only say once again, thank you very much for your time, for your presentation, and hope we can meet in the near future.
Indeed. Thanks for having me. Hope in the near future we can meet in person, all of you.
Yes.
It was great.
Yes, we'll definitely organize something for you in Brazil. Mazi, thank you very much. And to all the audience, bye-bye. Thank you very much.
Bye.
I'll see you the next talk. Beleza.